Good morning. Let's continue talking about this idea of standard deviations. Remember last time we had talked about these control charts that allowed us to figure out when things were behaving abnormally or when they were under control. Today we want to explore that a little further. In particular, using the population mean, using the population standard deviation, we want to calculate what we call a standard score. Think of it this way. It's very easy to talk about maybe, centimeters or kilometers, or in America they like to use inches and miles. But depending on what you're trying to measure, you'd like to have a different type of units. And I think also a lot of the allied health students enjoy discussing things that they call dimensional analysis. You're trying to convert things to the right set of measurements. The z-score is a standard score. And what it does is it takes one particular person, one point, one data point, and it compares it to the population mean, mu, and the population deviation, sigma. And once you do that comparison, you're able to find what we call a standard z-score. And the standard z-score is very interesting because we can look up in a chart how much area under our normal curve, using the empirical probability rule, we've got. Think back to previous chapters where we've discussed Chebyshev's rule. And remember, Chebyshev was a little bit unfortunate, cool as he was, because it tells us that we just have at least so many people must be in a particular range of standard deviation. We don't know how many at most there can be. We've just got this minimum cap, because Chebyshev's works for any data. But if our data is normal, and we calculate a z-score for it, then we can compare it to a normal curve. And remember, with the empirical rule, the normal curve had much more precise areas between 1 and 2 and 3 and so on standard deviations. So this gave us a much more powerful idea of the percents involved. So again, our idea is to convert random raw scores of different things into a single z-score. The goal being, we would like to take that z-score and use it to look up standard deviations. I don't know, sigma 1 z-score, 2 z-scores this way, 2 standard deviations this way, and so on. We would like to use this to find the area under this normal curve. Is our goal as we look up the z-score here. And the idea behind the z-score is that when you recalibrate under z measurements, you don't have mu as some random number. Instead, you recalculate it so that mu is actually 0, and then your z-score becomes 1 standard deviation, 2 standard deviations, or -1 or -2, and so on. You're able to get a very excellent measurement that works no matter what your data is, because you've converted your data from its units, whatever those may be, to standard units. And that means you can look up the area under the curve. As I've mentioned before, if you take calculus, you're not very afraid of looking up different areas under different curves. But we're here in statistics, and our goal is to have a single chart, a single calculation that will work. Our process in this class is a little bit old school, I admit. What we're going to do is we're going to always calculate a z-score when we're interested in the percents. And then we're going to use our z-score to look up things in a chart. And when we look up things in that chart, we'll be able to figure out the percents. In particular, in this book, we use what we call left-calibrated charts. Namely, our charts start counting from the left, and they fill in area. So if you have a z-score of -1, if you look up a z-score of -1 in our chart, you'll find the area to the left of -1. People whose z-scores are more negative than 1. Some books do right-calibrated z-score charts. If you want to use Excel, which is maybe an interesting program, you don't have to look up your z-score in a chart. Excel will just tell you the area, again to the left with the settings I'm going to talk about in this class, and the function is equal norm, norm, .dist, norm distribution, the normal distribution, this one that's bell-shaped, and you have to give it 4 things into the Excel function. You have to tell it the x value, the 1 point that you're trying to compare to the whole population. You have to tell it the population mean. You have to tell it the population deviation. and then you have to tell it two things, either true or false. In this class, we're going to use the letters true, T-R-U-E, if I can spell, and you type in T-R-U-E, and that tells you that you're wanting to do a left-tailed test, and that will make Excel and this chart work perfectly. That way I can mostly talk about things using the chart, and then we can use Excel if we want to. All right, so that's our idea. Let's see how this exactly works with what I think is maybe the traditional example. Here we have two classes. I teach both face-to-face and, of course, online statistics courses. Let's say that I have two different students, one in each class. Here we have Jane is online and she scores an 82 on her midterm. On the other hand, Mike is in a face-to-face class and he scores an 80 on his midterm. Can I say that Jane is the better student because she scored higher? And maybe better is a harsh word, but did Jane score higher? Is that a fair thing to say? And the answer is, well, we don't know yet. There's all sorts of things. They tell us a little more information here. Jane scored an 82, but the average for online students taking a statistics class is 78. That's the population average for that population. Notice I'm not talking about just Jane's class. That might not be a reasonable population to discuss. Instead, we're talking about all online stats students, and maybe that's the population we're looking at. The standard deviation for this is 20. Online students seem to score rather high on average, but the deviation is quite large. There's a lot of wiggle in there. We seem to have maybe a very turbulent data set. Contrary-wise, Mike, who's a traditional student, is scored an 80 on his exam, his midterm exam. That class is a little more traditional. The average score is 70. And it's got less variance. Incidentally, many of these numbers are made up, and of course Jane and Mike are not real students, but I can tell you this, online classes do tend to have a wider range of values. They tend to have a higher deviation simply because I think that in a face-to-face class, students are asking their professor a few more questions, and so we all sort of end up coming to a little bit more of a cohesive whole. What is fascinating to me is, with this recent round of videos, I'm seeing that at least the quizzes in my online classes versus face-to-face are all norming quite a little bit more. There's something I think about someone talking to you that makes it make a little bit more sense. So, who's earned the higher score? That's one question. Can we just say Jane, or is Mike possibly scoring higher than Jane on some absolute measure? Secondly, does it make sense to say that the exams are out of 100 points? Do we know that from the information we're given? And lastly, which student earned a B? Both of them seem to be in the 80s. Should they score a B, or is one student definitely in the higher category than another? These are very interesting things to talk about. I think it matters a lot to students, and of course it matters a great deal more when you stop thinking of maybe just students and start thinking of, well, what do A, B, and C mean in the real world? Well, you want employees who are performing top-notch. So let's first of all try to see how many of these we can answer with common sense without math. So are the exams out of 100 points? The answer is not enough information. On some sort of absolute scale that we might want to talk about, it would matter if the exams were out of 100 points. I've given students back exams that had 20 points on the front, and they freaked out until everyone remembered that it was out of 21 points total. 20 over 21 is quite a good score. On the other hand, you could give somebody a test back that has 120 on it, and that's not very good if the total exam is out of 500, 600 points. So you do have to worry about hundreds of points and what the whole exam could be. Excuse me. However, in this case, we don't care. There's not enough info to decide, and luckily statistics doesn't really care about what the high score could be. It cares about what your score is, what the average is, and what the normal amount of deviation is. That's what the z-score is going to allow us to calculate and discuss. So the answer is, well, we don't know, but we don't care. And which student earned a B? And that's a little more tricky question, and we're going to talk a little bit about that before we actually calculate out a z-score for this. What does a B mean? Well, under traditional measures of grade things, I think that we have this normal scale here, and I do mean traditional in America. I know that Australia uses a totally different grade scale that I honestly don't understand. And Canada tends to have a grade of A, B, C, D, E, I guess, in here that's in between D and F. Notice we skip a letter here in the United States for reasons that are kind of beyond me. But if I was going to attach labels to these in words, I would probably say that C means something about average. That's the average grade in a course. The average grade that represents decent understanding. This is pass. And maybe that's a strong word, but D is usually pass. I think some people do say the terrible thing, D's get degrees, and I don't know that I can encourage that. But in general, D is not a failing grade. That's reserved for this. B then tends to be very good. And A, of course, tends to mean exceptional. In fact, at most schools and universities in the United States, if you look somewhere deep within the student catalog, you will find these verbal descriptions for the letter grades. And again, these are rough. Don't take my word for this pass. I have this great fear that you'll be like, oh, that means I passed the class, and then you can't take the next one or something. Or your degree requires C's for everything because you're in some nursing field and everyone has to be at least average to be allowed to stick drugs into people and heal them. So, if we have these kinds of descriptions, well, these sorts of descriptions kind of make sense on a normal curve. Because here is mu, and that means average. And so probably if you go a standard deviation in one direction or another, this chunk in the middle is probably something along the lines of where you might expect to see C's. And maybe you see C on the right and D on the left, but roughly that's what we're talking about. This is an average score. So a score that's in this average range might be called a C. And a score that's in this just a smidge below average range might be called D, a pass. And then if you go another standard deviation up here, you would say, well, this is very good. And then if you go even further, you say, well, this must be truly exceptional. And think back to our control chart from the last time. If you're consistently scoring above 2 standard deviations, we say that's out of control. But in the case of somebody learning something, that's probably a good thing. And then we kind of tend to lump everything on this direction and say, well, all of this, you didn't really learn all that much if you're scoring in there. So this might be one way to try to organize this question. Now, of course, if you're taking this class with me, don't panic. I don't make you fight survivor style for your grades. Instead, I do what's called a normal 90, 80, 70 scale. And of course, I attach percents because I don't always make my tests out of 100%. But if these were out of 100, then this 80 and this 82, of course, in my world, would be called a B. And I wouldn't worry about doing a curve. Which brings up a great point. I think I said sometime in the video at the beginning of this course that eventually we would talk about what kind of grading scale we used. And in fact, I use a traditional 70, 80, 90 scale because I want you to be competing against you. And I take some extra time when I design a test to make sure that if you understand all the material exceptionally well, then you should be able to score a 90%. It takes extra time to design a test like that because I have to understand how students work. I have to understand how people think and learn, and I have to build a test so that, in general, I would expect somebody who is very good in understanding this class to score an 80 to 90. And if somebody was exceptional at understanding this class, they should score a 90 or higher. That's somewhat tricky to do. But I dislike curving because, well, you'll see what's going to happen in a second if we were to just do a strict curve. I think often students ask their professor, do you curve? And some professors smile kindly and say, yes, I do. And that's not always a good thing, as we're about to see here. So maybe this is a way to organize it. This is called a standard bell curve, I think, for grading. These are the common-ish letter descriptions for A, B, C, D. So let's take a look at how Mike and Jane fare. Under my scale, in my class, because I'm a kindly person, both Jane and Mike just earned a B on their test if they were out of 100 points. However, under a normal curve, who did better? Who's more competitive in this world we live in? Well, we have to calculate the z-score. And the z-score says this. We're going to take the 1 point that's attached, we usually think of as attached to a person, in this case a score. So let's calculate the z-score for Jane. I'll call it z sub j, j for Jane. Jane scored an 82. That was what she earned on her exam raw. For Jane, the average score, the mean, is 78. And let me just take a moment to say that from here on out, I know earlier on we made a difference between mean, median, and mode, and we said that the arithmetic mean, this guy, was what we were going to generally talk about. However, when you're looking at this, we tend to use the word average for all these things, and from here on out in this course, I will do the traditional statistics thing, and I will say average. When I say average, unless I specify, I mean mean, the arithmetic mean in particular. So we have 78 as the mean in Jane's class, and we have sigma, and for her, sigma was 20. We can go ahead and calculate this out. Again, as a reminder, your calculator does have a very convenient ability with this fraction button right here. You can hit that, and then we can type in 82 minus 78, scroll down and hit a 20 there. And then it's nicely entered in exactly the way it's showing up here on the book. And we get 1/5, and if you hit the wiggly equals button, you will get yourself, of course, 0.2. That's Jane's z-score. That's her normal point system. Where does this live on the normal curve? Well, here's 0. Here's 1 z standard deviation. Here's -1. Here's 2 standard deviations on the normal. Here's 2 in the positive direction. Jane lives here at 0.2. What the z-score does is it converts Jane's raw score of 82 into number of standard deviations away from 0, where it's renormalized everything to have a normal score of 0 be average. It's recalibrating everything around this population mean, and that way, if you plug in 78, you'd have 78 minus 78, and that will give you 0. So it's realigned Jane's score so that instead of the average being at 78, the average is now right here at 0, and we can have a perfect bell curve. Here's Jane. Let's calculate the same score, the z-score, now for Mike, so I have z sub m. Mike's a little different. His raw score was an 80. The mean score was a 70, and his standard deviation was 10. 80 minus 70 is 10, and over 10 equals 1. Mike's score is here. We can now find out a couple things that might be interesting. First of all, just looking at this grid, I can see that despite the fact that it looks like Jane scored higher, the fact is that she was in a different environment, possibly even taking a different test, and on her test, the usual performance was 78, and 82 wasn't all that impressive. Furthermore, because in the environment Jane was, there was a lot of turbulence in the data, you'd have to do a lot better than 78 to be significantly different from your peers. Jane's doing exactly like everyone else in her class. We might call that kind of performance average, in which case we might say C. On the other hand, Mike is doing very different from everyone else in his class. People in his class tend to score a 70. People in his class tend to be only plus or minus 10 away from 70. That's a standard deviation for them. And so Mike, scoring an 80, has in fact scored an entire standard deviation superior to the rest of his class. That puts him in here, right at the bottom maybe, or right at the cutoff of between C and D territory. So, if I was a professor who had promised his students he would curve, as I can promise you many of my face-to-face students usually ask me about, and they want this. They say, will you curve the class? And I always tell them, no, here's why. I would probably have to assign these letter grades to these two. And this would probably make Jane feel very badly, especially if she knew that her score was 82 and Mike's score was 80. She would say, that's not fair. I kind of tend to agree with letter scorings because it's not about how you are competing with your peers. That's one important aspect of life, but that's not what academia is about. Here we're trying to just develop each person individually. And so that's why I tend to do the 70, 80, 90 scale, and I don't curve. These are their raw scores. What we're also interested in is something else. When I say that Jane scored 0.2, what do I mean in terms of how many people did she score better than? That's this idea of percentile. And we can look this up in our chart. So let me talk a little bit about our chart. And I think if you got a paper version of your textbook, you'd have this chart. On my website, I think I have this released under, I think we call it something like Stats Crib Notes or something. It's a pretty common chart, and again, we can use Excel if you don't have a paper copy of this chart. But these charts are pretty common. And here's how they look. I'm going to stand over here so you're not seeing like one side of my blown up face. This is a left-normed one, and so you'll notice that everything starts at the left and it starts shading from the left, and we'll talk about some pros and cons of that a little later on. But what you have down here is you have a z-score, and you have the first point as well as a point right after the decimal place. So you've got a 1 decimal place here. And then, notice on the top here you have these 2 decimal places. That first 0 is of course going to be filled in with whatever point you've got here. So if I look at this point right here, what I would be finding is the z-score of negative 3.44. So I get negative 3.4, and then I go over till I get that last decimal place, and then I would say this is the area to the left. In our case, Jane had scored 0.2. That was a positive 0.2. So I would stop on this chart, because I noticed that here on this one it goes all the way to 0. I would go to a little further on my chart where we have positive z-scores, and I would look up the positive score 0.2, and remember this goes to several decimal places, at least one after this, so I'd actually look up the number 0.20. And if I do this for you, 0.2, and then we go to 0, and we see 0.5793 is the area that we're looking at to the left. So for Jane, 0.5793 people score worse than her. Well, that kind of again supports this idea of a C. She's a little better than about half of the people. She's average. She's in that middle category, that middle territory. On the other hand, for Mike, his raw score for Z's was a 1. If we look up a standard deviation of 1, we go down the Z column for 1.0, we go over to 1.00, and we find 0.8413. Mike has scored higher than 84% of people who took the test. Mike has done much better than average. whatever average might be on this test, he has scored exceptionally more than them. And so this is exactly the type of reasoning why we would say Mike's not just done an average performance, he's done very good. Many people have scored much lower than him. Incidentally, this is how you calculate things on standardized tests, and that's in fact what a standardized test means. If you look at things like, I don't know, the SAT or the ACT or MCATs or LSATs or GREs, and what was the other one that I just took, a major field test for an MBA degree. If you look at all these types of tests, they usually have scores that range from like 200 points if you write your name on it to 2,300 points for a maximum top score. And people get all sorts of scores in between there, but you don't really look at your raw score. No one cares. It doesn't mean anything. Instead, you look at your percentile, and you see what percentile of people were scoring less than me. And if we draw this a little bit nicer, maybe here, what you would see, here's 0, here's 0.2. When I say 0.5793, what I mean is that, remember, the total area under the normal curve equals 1. There's a 100% chance of something happening. When we talk about a left-normed table and a left-normed lookup, or when we use norm.distribution and put true in it for cumulative in Excel, what we're finding is the area to the left of this. All the numbers, all the people, what percent of the curve is less than 0.2. So we're finding all the folks who would have scored raw scores that would have given them z-scores of smaller than 0.2. So we're finding everyone that you're sort of got below. Sometimes we're curious about the flip side. What if we wanted to know how many people scored higher than Jane? Well, we could find that because, remember, the total area under the curve has to be 1. So if you have a left distributed table, you find the area to the left, but if you want to know the area to the right, the people who scored higher than her, well, you just have to do 1 minus the area to the left. If we do that subtraction, 1 minus 0.5793, you find that you have, for this right area, 0.4207. Again, this is giving me more evidence if I was going to use a bell curve that I probably would not really be thinking about awarding a B to poor Jane, because 42% of people do a lot better than her. Maybe it's not a lot better, but they do better. They score higher. She's right in the middle. She's doing perfectly good stuff, but there's people who do it faster somehow and do more of it. If we take a look at Mike, we find a very different scenario. For Mike, his score was a z-score of 1. So if we looked up, we'd find that to the left, we had 0.8413. .13% of people score a little lower than Mike, some ways. If we want to look at how many people score higher than Mike, we would do 1 minus that. And 1 minus 0.8413 gives us 0.1587. In other words, only 15.8% of people, 15.9 maybe with rounding, scored higher than Mike. And that seems pretty good reason to say Mike's in this very good performance category. Is he exceptional? No, there's 15% of people that are better than him by this score measure. And so if you were looking at this, another way to say that is, out of every 100 people, there's about 16 people who score better than Mike. So Mike really isn't exceptional, but he's very good. On the other hand, out of every 100 people, there's 42 people who score higher than Jane did on her test, and so we'd say, well, Jane's about average. She's in the middle. So, we've looked at this idea that we can take a raw score, a single point, and compare it to the population mean and the population deviation to calculate a z-score. And what a z-score does is it converts your raw score that's doing who knows what under its measurement system. Maybe it's an 80, maybe it's an 82, we don't know. And it turns it all into number of standard deviations away from zero that you and that particular 1-point score happen to live. And that's a very powerful thing, because what it does is it allows us to figure out what the area is, looking it up on a normal chart that's already calculated the areas out for us, or looking it up in Excel that's already calculated the areas out for us. And that means we can get a sense for Jane and Mike whose scoring is very good, who's scoring average. If we had a different set of points that we were comparing, we could find out, what do I really mean when I want to say who's scoring something that's truly exceptional? There's several exercises in your book, and recommended ones that I do online, where they give you some practice looking things up at the chart. Go ahead and look through any chart that you've got, and you can look that up. Of course, we don't have to use a chart. We can just type in the raw scores here and get those numbers. So I'm not always very excited about looking things up in the chart. I'm interested in interpreting things. And so I wanted to do one last example where we focus on a different direction to the interpretation. Let me erase some things a little bit here. Let's ask the flip question. Let's send Jane and Mike off to live their happy lives. And let's consider a slightly different scenario. It was kind of sad for Jane and Mike because they had no more control over the situation. They'd already done their study, they already took their test, and now we were just figuring out what happened. But suppose you want to do something different. Suppose you're getting ready to sit down to some standardized test, and you know that you want to score in the top 80%. So the question might be, I want to do better than 80% of people who take this test. Okay. How do you do that? Well, there's quite a few things you can do, and there's quite a couple of ways we can look at this. But the idea is this. We would like to look in our chart. We would like to find 80% of the area. We don't know what this number is, but we do know that we have to shade in 80% of the area here. We happen to know that Mike, who just scored a z-score of 1, had 84% to the left of him, so I'm kind of expecting a z-score a little bit smaller than 1, obviously a little bit bigger than 0, right? Somewhere in between here. We want to get 80%. We would like to find a way to look this up, and if we could look up this 80% in our chart and figure out a z number, we would then like to figure out, okay, how much does the average person score? What's the standard deviation? And then we can back solve for x. Now this is not an algebra class, but that being said, your book tries to make you memorize 2 formulas, and you don't have to. We know from algebra that you can multiply both sides of an equal sign by the same number. So if I multiply both sides by sigma, on the right side, divided by and times cancel. So I'm left with sigma z equals x minus mu. And I can also add mu to both sides. And I get a new formula. Mu plus sigma times z equals x, where this is, of course, the population average. This is the standard deviation. This is the z-score. And this will give me the 1-point value. In this case, we plugged in the 1 point, we found a z-score. But if we want to do better than 80% of people, we have to work our way backwards. And here's entirely where the chart can be quite useful. Incidentally, Excel will also do this. It's called normdisc inverse, I think, something like that. Start typing in norm.d, and I think that suddenly the inverse function will also show up there, and it will allow you to plug in the other things, and it will give you your z-score. But let's take a look at this. If we want to score better than 80% of people, we need to find in the middle of our chart the place where 80% comes into play. We just saw for a z-score of 1 that we had 84%, so I'm going to look a little higher than this, and I find the closest number to 80% I can find. Here it looks like 0.823. That's pretty close to 80%. If I look left, I see 0.8, and if I look up, I see 0.05, so I know that 0.85 is going to be my z-score. That makes sense because at 0.2, when we calculated Jane's z-score, 0.2, and these are standard, remember, at 0.2, Jane had about 57% of people less than her. That's not enough. We want 80. And at 1.00, Mike had about 84% people less than him. So we're expecting that we want a number between 0.2 and 1.0, and we found it. So that common sense kicks in. This is the z-score we're looking for. If we want to score 80%, in particular 80.23%, higher than everyone, this is the z-score that we would want to score at. Okay, what else would we need to know? Well, if you want to beat 80% of everyone, you have to know a little bit about how everyone else does. So you would also have to know what's the average for everyone else. And you'd also have to know what's the normal amount of turbulence in that data. What's sigma? And you can do this with anything. Do a quick poll. You want to score better than 80% of the students in the class? Ask people, how often do you study? What's the average studying? Poll several students in the class, find out how many hours everyone studies. If you take all those pieces of time that everyone studies, you can find the average if you add them all up. You can also then find the standard deviation. And then you know how much difference there is. I would guess, just based on previous polls that I've done, that for my statistics class, I know that I recommend about, 13, 14 hours if you look at my website. However, I tend to find that students, on average, spend about 5 hours of studying. That seems to be average. The standard deviation, though, is pretty wide. It's about 2 or so hours. So let's say we go with that. The average student were to study 5 hours, and the standard deviation was 2 hours, and I'm talking about per week, of course. Then we could plug everything we need into this formula here. Because we know the average is 5, we know sigma is 2, that's in rough numbers, we know the z-score is 0.85, that gives you x, and so maybe we can take 5 plus parentheses 2 times 0.85, close the parentheses and hit equals, and we find 6.7 hours equals x. So maybe that tells you you have to study 6.7 hours. But of course, that's an average. And the one downside to doing the grade calculations that I do is I won't take your 82 and turn it into a C. You don't have to worry about that. But you do have to worry about the fact that it's not good enough to do more study time than 80% of your peers. You have to do enough study time to actually score an 80% on the test to get a B. And that's where I think that my 13 hours is about the minimum that I think you probably need to score a 70. So if you want to do a little better than that, maybe you have to increase that by standard deviation or so. Which is still going to be about 2 hours, so 13, 14, 15. Probably if you're in the 15 to 20 hour range, I would probably imagine that kind of student scoring a high grade in this course. All right, I think I'm probably out of time for today's lesson. So what have we talked about? We've talked about the standard z-score, and we found at the end a way to recalculate this out so that you could have the ability to plug in averages and percents and figure out what you need to do. Incidentally, you can do this as well, not with hours, but with actual scores. Particularly, this can be helpful for standardized exams. You can be saying, what score should I be looking for? We've also talked about this idea of percents and the fact that everything's to the left. And I mentioned that you can either look things up in a chart, which you should get comfortable with probably, but you can also use Excel to look things up. So I think that's what I've got for today. Until next time, be safe, and I'll see you in the next section.